Okay, so let's get started. So there were actually so many troubles before we start. So actually the camera took so long to get started. Also there was a network disconnection a few minutes before the lecture begins. So it may happen during the lecture. So if you think it's happening, let me know immediately. Okay, I hope it's okay. And so here is today's plan. So I think I'm going to spend a little bit of time speaking about the OpenMP for GPUs. So far, when we talk about programming on GPU, it was CUDA, but actually you can use OpenMP for GPU, and it's kind of emerging, and I think it's good to know. And I will hopefully finish this part relatively quickly, and I'll give you some time to work on this OpenMP for GPU notebook. And also, if you like to do so, you can spend some time working on the assignment PD08 MM. So I'm planning to have a fair amount of time for the exercise. And if the time permits, I will go to the next topic about the memory performance. Okay, so let's get started with this OpenMP for GPU again. Okay, so this is actually the new topic I have never talked about in a previous incarnation of this course. This slide is short, and I can hopefully finish this relatively quickly. So almost everything is actually in the Jupyter notebook, so there's no much point in my speaking too much using slides. So I suggest I like to say this. So recent OpenMP actually supports something called offloading. So do things on GPU, and it is the thing around something called the target directive. I'll get to it shortly. And again, you can see the details on the official homepage and the specification. Okay, I think that's it for this slide. This is definitely the thing you will learn in the Jupyter notebook, and also, it's somewhat different between from one compiler to another. So you just learn on the fly. But so for LLVM, you give these two options. So not just -F OpenMP, which you have been giving to compile it for multi-core, but also this -F OpenMP targets equal NVPTX. That's difficult to remember, but it's basically NVIDIA PTX. PTX is basically the something like an assembly language for GPUs. And for NVIDIA HPC SDK, so you use either NVC if it is a C program, or NVC++ if it's a C++ program. You give -MP. This is the OpenMP. And in addition to saying this is an OpenMP program, you say the target is a GPU. So that's what you need to specify in the command line. And here's a short overview of the directives you're going to learn. Primarily in the Jupyter notebook. I don't get into too much into any of them. But basically, so you need a directive to move control from the host to GPU. So something that get execution started on the GPU. So for this, you have something called the target directive. And also you need to parallelize something. And you have already actually learned this parallel and for. These are for multi-core CPUs, but they are also usable for GPUs. But when you do things on GPUs, you actually need to have another layer of something similar to parallel and for. So they are called teams and distribute. So teams is somewhat similar to parallel in the sense that it creates many threads essentially doing the same thing. And distributed, not distributed, distribute. Distribute is something like a for. So it takes a for loop just below this distribute directive. And the primary purpose is to distribute loop iterations into teams you have just created. So it's pretty similar to what you did with this parallel and for multi-core. And the legitimate question is why you need both. So why can't you just keep using only parallel and for to do things in parallel on GPU? I think it's totally a legitimate question, and I don't exactly know why, but you need to think then teams and distribute just another extra layer outside parallel plus for. But I come to this point later a little bit, but I don't know the true reason. So you can think of alternative language design in which you do everything with just parallel and for. And another thing you need to master is how to move or synchronize data between a CPU and GPU. So in the CUDA programming, it was totally manual. But OpenMP has much more convenient primitives for that. They are called something like target data. So about the reason why you have two layers to express very similar things. So in one layer you have teams and distribute, and the other layer you have parallel and for. Well, I don't know the exact reason why there have to be two layers, but just as an implementation node, it looks like a single team. So things you create using this teams primitive corresponds to a single thread block. So you can think of teams directive as a primitive to create many thread blocks. And in each thread block, you start only a single thread. And a thread, so this is what you create by parallel directive. You can think of it as roughly corresponding to a single CUDA thread. So in a way, this teams and parallel hierarchy represent what you have in CUDA programming too, the thread block, and so many threads within each thread block. Well, again, but if the OpenMP is meant to be a higher level programming, so higher level than CUDA, it is totally legitimate to ask why still we need to export both to the programmer. Well, why don't you have just a single layer exposed to the programmer and the compiler and the runtime system does everything else? It's a totally legitimate question, but it's not the way it works, at least for today. So this implementation node, well, it's not actually clearly specified anywhere in the spec. So even if you look into the spec, there's nowhere it says, okay, so this team is a thread block and this thread is a CUDA thread. But this, understanding, well, at least helps you understand why things look this way, look somewhat redundant. So in the notebook, you are going to learn a few idioms, and you can easily get confused. So I am confused too, initially. So in this slide, so rather than getting into each of them, taking so much time, well, I just leave these details to the Jupyter notebook, so self-learning. But I just point out in this slide only that these are actually frequently used in combination. So the very frequently seen idiom is something like this. So pragma OMP, target, teams, distribute, parallel for. It's kind of insane. So there's so many keywords, but they are nominally a standalone, independent, not necessarily orthogonal, but somewhat orthogonal directives. So each having its own meaning. But they are often used in this combination. Well, basically, target says, okay, I want to move the execution to the GPU. So it's essentially saying you want to execute this loop on the GPU. And teams distribute parallel for combine, but they are essentially saying the same thing. So you want to distribute iterations of this loop to threads and thread blocks. And in other cases, you want to somewhat separate teams plus distribute. Distribute. I keep saying, I somehow keep writing distributed. So teams plus distribute and parallel plus for. So you want to make them separate. So like this. So you have an outer loop, which is parallelized by teams and distribute. And you have inner loop that is parallelized by parallel for. So this is another common combination if we can. So both are actually similar to launching a kernel doing this iteration. But this, well, either of them is somewhat easier to maintain. So you don't have to, first of all, adjust thread block size. So you don't have to specify the thread block size. And the program becomes orthogonal to the actual thread count. So in CUDA programming, so you somehow specify the thread numbers and thread block size. And what you typically do is just to give a single iteration to a single CUDA thread, but it's not necessarily the optimal always, right? So when you have, for example, so many more iterations, so you may need to assign multiple assignments to a single thread. If that happens, CUDA programs quickly become somewhat ugly and awkward. So you want to maintain the same structure no matter how many threads you end up creating. So this is really a benefit of using OpenMP instead of CUDA. And data mapping is another thing that benefits much more from using OpenMP rather than CUDA. So let's remember what kind of things you need to do when programming CUDA. So data management, moving data back and forth between CPU and GPU was actually a major headache when you do some serious programming using CUDA. So in CUDA, the only sort of more or less transparent data transfer that happens is argument passing. So when you specify argument like this, these data are transparently moved from host to GPU, right? So you don't have to do too much to send these data to GPU. But other than that, everything else is almost manual, right? So for example, sorry, so it is a typo. So getting the result calculated in GPU and back to CPU is already painful, right? So this kernel function needs to be a void function that cannot return anything, right? So if you return some result from GPU to CPU, you need to do something like this. Another typo. So first you need to allocate the memory on GPU, and RDEV becomes a pointer to it. And you pass the RDEV, not R. But this kind of mistakes happens. So you pass this RDEV as an argument to the kernel function. And the kernel function writes results to the address pointed to by this RDEV. And you get the contents, so the data pointed to by this RDEV back to CPU by calling CUDA mem copy, right? So it's already painful if you need to do every time you run your kernel. And well, actually, your program is likely to maintain somewhat more persistent data. So not just getting the result back from GPU to CPU. So in that case, well, conceptually, you need to have two versions of logically the same data, right? And these addresses, so address of them are different, right? So you maintain two pointers to logically the same data. So CPU version, GPU version. So just like this RDEV and R. So R pointing to a CPU version, RDEV pointing to a GPU version. And from time to time, you need to get them synchronized, right, when necessary. So typically right before you launch your kernel and right after you launch your kernel. So data mapping feature of OpenP largely alleviates this painful procedure. So syntactically, it looks like this. So it's somewhat similar to the moving control to GPU. Which was just a pragma OMP. So I forgot to OMP here. So it was pragma OMP target. But when you move data between CPU and GPU, you have pragma OMP target data. And the important things are these clauses like map. Well, typically you use just a few map clauses attached to this target data directive. So this to A from B to C basically says, okay, so before you execute S on GPUs, you want to send the range of arrays, the Bth element, so from the Bth element to one element before the Cth element, so which is AB plus 1 to AC minus 1 to GPU before starting S. And when you say map from and say a variable name like this, so it can be, of course, an expression like this. But you can have an expression like this or just a variable name or array name. So details are in the notebook. But if you say from followed by some variables, then the result, the value in X is sent back from GPU, well, naturally after S is finished, right? So this way you can send something from CPU to GPU before S executes. And you can send some data from GPU to CPU after S is finished. And actually you can combine this to and from into one thing, like to from. So this is useful when you first send some data, input data to GPU, let the GPU work on this data and get the result back from GPU on the same address, right? So the address you just passed to the GPU. So operationally speaking, you can think of these two map clauses as directive to say, okay, I want to send data to GPU. I want to send data from GPU. But with somewhat more declarative way of understanding the meaning of these map clauses is that when you write something like this, well, you can think of this clause to be a directive to instruct that expressions of this form, A, I, and I is between B and C, become valid. Valid meaning, so when you do it on GPU, well, you get the expected result, right? So you get whatever you have, whatever you would have in CPU. So that's why this is called a map. So in a way, yeah, this expression is some correctly mapped on GPU. So it is available on GPU. This is what it is meant by this map keyword. And also by saying this map X, then yeah, X becomes valid. But in the case of from, the more precise meaning is that if you access X after S is finished, then you get the expected result. Expected meaning that whatever you have written to X in GPU becomes visible on the CPU side. And I explained this as a separate directive target data. So a separate directive from the original Pragma OMP target, which is for moving control from host to GPU. But actually, these map clauses can be specified also as a part of the target. I explained earlier, target for moving control from CPU to GPU. So the details you should learn in the notebook. And I think that's it for this slide. So as promised, so let's have some time to work on the Jupyter notebook. So I gave a new one, a PD09, just for learning these OpenMP for GPU things. And you can also spend some time on the assignment and ask questions meanwhile. So let's have exercise time until, let's say, 5:40. So something like 25 minutes. And you can ask questions using this opportunity, either about this one or the assignment.
So I just know if the data was correct or not.
So it says it's not
Yeah.
vectorized.
After this question, I don't really know how you know the number of cycles with this. Is it with a table? Something with inside?
Okay, so is the question about how to measure the number of cycles?
Mhm.
So I think it's automatically measuring it
Oh,
on behalf of you. So you just run
I
it.
thought it was your prediction, so that's why run it, and this is the prediction is here.
Okay, so the actual measurement and predictions are two separate things, right?
Oh yeah,
So measurement is just this, right?
this one.
Yeah. So
This is the
what is it? What exactly you are asked to predict?
size per iteration.
Okay, cycles per iteration, right? So cycles per iteration. So you so is this the first one, not even vectorized one, right?
Yes, the first one.
So so prediction is basically you can predict that the number of cycles per iteration by the latency of FMA instruction, like I explained in the lecture.
Yes.
And did you look at the assembly?
This is the assembly.
Okay. And did you locate the innermost loop that corresponds to the okay.
Yeah, we used and we did the
I'm not sure how you.
Okay, so you have a FMA here, right? And if there's nowhere else in which you have FMA, it should be the loop. Okay, so yeah, this is the loop, right?
Oh, this is Russia.
Yeah. So you have a label here, right? And you have a jump instruction going to this label. So this is the loop corresponding to the source code, right? And basically, what you ask to do is to look at these instructions, and based on the latency and dependencies, how many cycles it will take per iteration. But so in this particular case, you can do that just by looking at the instructions and basic knowledge about the latency of FNR. So say in 4 cycles. But you can actually use the tool I just introduced in the end of the last week's lecture. So LLV and MCA.
Yeah, but I thought it was later.
Yeah.
This one.
Yes. So you can apply this one to the earlier problem.
And
So
give you the latency and the. Okay.
it's like the yeah,
About the lecture, I'm not sure because I tried to do something like the example that it was in time.
Okay, so yeah, in terms of the pseudocode, yeah, it should be something like this, right? But the thing is, so the C++ actually doesn't allow this kind of expression. So instead of writing something like this, you need to have some expression or some method to get these L elements, right?
Is it method? It's a for a loop.
No, so actually it's just a single vectorized load instruction. So if you have a pointer to the vector data, so you are manipulating. So for example, if you have scalar data called real, so you can define a vector of reals. Just like I explained in the lecture. So once you have a data type that represents a vector of real, then you have a pointer to it, right? And you dereference the pointer and get the vector of reals. So this is how you do it logically. And in terms of the program, I explained something.
Only if it comes from sometimes, yeah. Yeah, or not,
So what you need to do is basically something like this. So so take any expression, or for example, the variable, take the address of it and cast it to pointer to the vectors. Pointer to a vector, yeah,
Okay.
and dereference it. Using
So this is same as this.
Right.
Okay.
Right.
Thank you very much.
And actually, in the Jupyter notebook, I have already defined the method that just does that. So I guess. Okay, this one. So it already defines a method called V.
Really?
Yes.
And then
So if you so instead of you accessing a parent ij, you say a dot v parent ij, and then you get exactly this.
maybe she tried.
Because you say like this.
Okay.
It's part of this
So
one.
now I can use this.
Yes.
Okay, thanks.
So it gives you a vector that B gives you a vector somehow below it. And if you do that as with one array and the you can Okay. So let's get started again. So I'm gonna talk about the next thing, which is about the memory. But I got a question. So the question is there any async way to use OMP for GPU? I think the async way, I guess you mean that there's a way for CPUs to move ahead before GPU is doing something else. Yeah, I think so. Yeah, although I haven't used it by myself, but this is just the OMP spec about this target construct. And you can specify many clauses, one of which is this no wait clause. So I guess the effect of this is the CPU doesn't have to wait until this target region is finished. So I guess you check yourself, but I think that's what it is. Yeah. Okay. Okay. So then. Just moving on. So the new Jupyter notebook you're working on is about using OpenMP for GPU. So it explains each of these directives I just lightly mentioned in the slide from target to teams and distribute. And the other thing is a data mapping. So you can master each of these. And in the end, you can write a GPU program with a relatively small amount of effort. So in the final problem, you are asked to write a GPU program that gets the calculated summation of arrays. So the original program you were given that just works on CPU is this. So you just have a vector and each element being initialized with 1 and the call a function that calculates the summation of all these elements, whose implementation is as simple as this on just a CPU serial call. And of course, you already know how to parallelize it using OpenMP for multi-core. But this time you are asked to do it on GPU. But actually in this final example, I hope you are pleased to learn that this is very simple. Well, just adding a single line, you can make it work on a GPU. But getting performance is actually another thing. But I hope you guys go through all these elementary concepts and finally solve this problem. But please do know that it is that easy. Okay, so. So is there, okay, so another question I just got is there an advantage to use parallel over distribute? Well, actually, it's not so much about which one is better than the other. So basically, you need to use both almost always. So if you use only teams and distribute, you end up with only a single thread in each thread block in CUDA terminology. So then, so if you use only a parallel, then I guess, well, so it's actually not specifically written in the spec, but what actually happens, at least in one implementation, is you end up with using only a single thread block. So both are actually necessary to fully utilize the GPU. Did I answer to your question? Okay, so with that said, you can actually play with, using both parallel and distribute, and only parallel and only distribute by yourself and see what happens. Okay, so let's get to the next topic. Which is about memory. So actually, there are so many topics in this slightly complex topic. So as the okay, so here's the introduction. So far you have learned so how to parallelize things across cores and on GPUs too. And on CPUs, how you vectorize or utilize simile instruction within the core, and also instruction level parallelism. So these are combined and to get good performance on CPU. So I didn't actually dig too much into how to get good performance on GPUs. So if I have time, I'll get to this. But just for the purpose of talking about some different things in a limited amount of time, let's move on to a very different topic, which is about memory. So, so basically, these things are how to utilize processors efficiently. But in actual program, another critical factor you have to know to get good performance and to understand program performance is how you data access, how you access data. So why data access and talking about the performance of data access is so important. So first of all, so it's very obvious that if you do not have any data, you don't have to compute. So no data, no computation. Well, of course, you can think of a program that generates data by yourself only from a small number of configuration parameters. But basically, the data comes from somewhere else, right? So you in a broad sense, you always process data when you do some computation. So this is sparse matrix code I have just I have shown several times during the course. So here you are accessing data. These expressions also access data, right? And this is dense matrix multiplications, matrix multiplication, and these are all data accesses, right? So any computation involves a fair amount of data accesses, right? And it's not the only reason why talking about data access is so important. So accessing data is sometimes far more costly than the calculation itself. Well, it is actually typically much more costly to access data than to do some calculation. And yet another reason why accessing data is so important is that the cost of the same data access instruction significantly depends on the where that data is actually coming from. So those are similar expression in terms of C, right? So they are all array indexing expressions, right? But so even in the instruction level, they all look very similar, and many of them are just load instruction. Well, some are actually register access instructions, so they are not load instructions at all. But well, So with this register access instruction as an exception, all others are exactly the same in terms of the kind of instructions you are using. But actually, where data are actually coming from significantly differ depending on the circumstances. So sometimes data is coming from caches. Sometimes data is coming from main memory. And in the context of multi-core GPU, the data may be coming from another processor's cache. So some communications may be happening invisible to you. So in terms of the instruction, they all look the same, just accessing some addresses using load or store instructions. So there's no way you can distinguish between the instruction that happen to get data from caches or instructions that happen to get data from main memory, all the way from the main memory. So understanding how processors work is in a way much more important and perhaps much more complex. So you cannot reason about the performance of a particular program just by looking at the instructions. So here is a conceptual goals of this segment. So one conceptual goal is to understand how processor, caches, and memory are connected and organized. Another thing is understand the behavior of caches so that you can reason about how much traffic your algorithm will generate, especially between main memory and caches. Well, in more general, among different cache levels, from L1 to L2 and from L2 to L3 or something like that. But most importantly, how much data needs to move between the main memory and caches. And with these understandings, you can reason about the performance limitation, the upper bound of the performance of your program due to the amount of memory traffic you need to generate. So this is very different from the performance limit that stems from the processor's performance, right? So the processor, of course, has its own limit, right? So like 2 FMAs per cycle. But the limitation I'm talking about, and I will be talking about in this segment, is something different. So by running this program, you need to move this much data between main memory and processor or caches, to be more precise. So the program necessarily takes more than this time. Something like that. So pragmatic goals of this study includes, so first of all, the latency. So to get a good sense of how many cycles it takes to get data from main memory and caches. If the data is on this level of cache, then the access latency is something like this. If you need to go all the way to the main memory, then the latency becomes much more. So you know it's much more, but how much? So getting a good sense of these numbers is one pragmatic goal of this segment. Another thing is bandwidth. This is how much data can actually move between main memory and processors or caches. So just like so you have to understand the latency and throughput of these instructions when we talk about the peak processor performance. You also need to be able to distinguish between these two, well, related but slightly different performance characteristics of the memory. So latency is again the time it takes to get a certain piece of data from the point you try to access that data. So it's basically some sort of round trip latency between processor and memory. And then the bandwidth is about how much data you can move from main memory to CPU in a given amount of time. So for example, if you want to send many data in parallel between CPU and processor, then you get the bandwidth, but not necessarily latency, right? So together with the distinction between latency and bandwidth, having relatively good sense about the absolute numbers in terms of cycles to get data from the main memory and caches is important. And another, somewhat cheap goal, but still pragmatically important goal is to understand what does memory bandwidth advertised as a processor spec actually mean. For example, if you look at the processor data sheet of a particular model of Intel CPU called E52698, it says the memory bandwidth is 68 gigabytes per second. It is what the Intel advertises as the memory bandwidth of this particular processor. Well, generally speaking, it is calculated by the following equation: 8 bytes multiplied by something called the DDR frequency, so the memory frequency, multiplied by the number of memory channels, which is essentially the configuration of a particular CPU. So this is the max bandwidth per CPU socket. And the CPU we are using in our environment, Howlett host, is Ice Lake Xeon Platinum 8368. So it has a DDR frequency of 3.2 gigahertz, and it has this CPU has 8 memory channels, and so all multiplied you get something like 200 gigabytes per socket. So this is what Intel would advertise as the maximum memory bandwidth of this processor. And if you have 2 CPUs on each on a single host, as our environment does, then you in theory get something like 400 gigabytes per second in the entire node. But what does actually mean? What does it actually mean? So just as the peak performance advertised by the processor vendors, like 3 teraflops or something like that, cannot be easily achievable just by ordinary C programs. This number is another thing that is advertised but is not easy to achieve in practice. So what does it actually mean, and how do you get close to this performance? It is another pragmatic goal in this section. So before getting into how the processor works around memory and caches, let me try to give you a little bit of motivation by speaking about the fact that many algorithms are actually bounded, so that the performance is actually limited by the memory performance, not CPU, not processor performance. So, so let me start by saying, so what does the fact that you have only so much memory performance imply for flops, the effective compute performance your program can attain. So the fact is that many so-called computationally efficient algorithms, so clever algorithms, do not touch the same data too many times. It's sort of obvious, right? So, for example, the typical algorithm that is called efficient is something whose time complexity is like order n, for example, or order n log n, right? So, and n is basically the size of the data, right? So if you have an order n algorithm, then the thing is that it uses a single element only a constant number of times on average, right? So if the algorithm, for example, accesses the same element n times, given the size of data being n, then you end up with order n square algorithm, right? So instead of order n, right? So the algorithms being efficient as order n, well, actually means that if you are given the n elements of data, a single element, each element is going to be manipulated only a constant number of times. So you don't access the same data too many times, right? And imagine that the total data, so this n, is much larger than cache. Then the algorithm's performance is often limited by the memory bandwidth, not or in some cases the latency, not processors compute throughput, right? So because these algorithms typically needs to touch every element at least once, right? And these data do not fit in the cache. So many of them are actually coming from main memory, right? You at least need to move the entire data at least once from main memory to the cache, right? To the processor. So this already dominates the entire execution time if the processor does not do too many things on each element of the data, right? So let's talk about a specific example, which is a sparse matrix vector multiply. We have discussed a few times as a running example. So this is what it looks like. So this sparse matrix is something like this. So these white parts are all zeros. So they are not represented in the memory. So they are not materialized in the memory. So instead, only non-zero elements are materialized in the memory. So which is this A.elements array. So the A.elements is the array of all non-zero elements. And when you are asked to multiply this A by another vector X, then what you do is just to scan the entire non-zero elements of A. And for each non-zero element, you also keep track of the row number and the column number of that particular element. So the Aij is the actual value of the element, and I and j are locations of the particular element. So after you get the row number, column number, and the element, the value of the matrix element, then you simply do this. So the element multiplied by xj and yi, right? So this is a very frequently used algorithm. And if you look at how much data it accesses, so it accesses, so let's say NNZ is the number of non-zero elements, then when each of these elements takes two integers and one floating point number. And if you assume that each integer is 4 bytes and the element itself is 8 bytes, double precision floating point number, then a single element takes 16 bytes. So when you run this algorithm, you are entirely accessing 16 NNZ bytes, right? So you necessarily have to access 16 NNZ bytes. And how much computation you actually perform after accessing all these NNZ elements? Well, you just perform 2 NNZ flops. So, in other words, it's just a single FMA per element, right? So you just perform 2 flops or just a single FMA per element. So in total, you just perform an NNZ FMAs or 2 NNZ flops. So actually, you need to access xj and yi, but I am just ignoring the cost of accessing these, or just only focus on accessing A. So how the performance of this computation is limited? Well, either by flops or the memory access. Well, it's actually clearly limited by the memory access. That the cost of bringing the whole 16 NNZ bytes from the main memory to the processor. So I'm assuming that this is much larger than the cache. So most of data actually from main memory. So to think about this. So let's consider how we can achieve the processor's peak performance. I just wrote Skylake X, but the details actually do not matter. So in any recent Intel processors, the processor's peak performance, which we are currently wishing to achieve, is 2 FMAs per cycle, right? So in terms of the number of double precision floating point number FMAs, it's 16. So assuming 512-bit SIMD instructions, then a single FMA can do 8 FMAs, right? So because the processor can execute 2 FMAs every single cycle, then it can perform 16 double precision FMAs per cycle per core. So in order to get this performance, a single core must access 16 matrix elements every single cycle, right? So it's very obvious, right? So whenever you get a single element, you perform only a single FMA. So it is accessing much data, doing relatively a small amount of computation, right? So in order to do 16 DP FMAs, well, you obviously need to access 16 matrix elements, right? Which amounts to 256 bytes right? So because a single element is 16 bytes, right? 16 by 16. So 256 bytes per cycle. So every cycle, every core has to get 256 bytes from memory. So let's assume for a second the processor frequency is 2.0 gigahertz, just for the purpose of simplicity of the calculation. Then, so you get 256 bytes every cycle, which means something like 512 gigabytes per second. And remember, this is the performance required for a single core, not the entire CPU. Well, compare this to the performance we have just talked about. So something like 200 gigabytes per second per entire chip, not a single core. So if you translate this into the required performance for the entire chip, well, so it gets something like, so it has something like 38 physical cores, then, so this should be multiplied by 38, something like 20 terabytes per second. So the actual performance is way lower than what it takes to get the close to peak performance for sparse matrix vector multiplication. So this leads us to the important notion of so-called memory bound algorithms. So actually, when we talk about the performance in the real HPC applications, high performance computing applications, essentially doing many simulations based on partial differential equations, we often encounter this notion of memory bound algorithms. So they are almost always talking about this. So let's say an algorithm performs C flops on n bytes of data. So we may be talking about the entire application, but more typically, we are talking about a single iteration of a single time step of the entire application or simulation. So essentially, the algorithm repeats doing C flops over n bytes of data. And let's assume it needs to access every element of the n bytes at least once. So it's likely the case, right? So if you do not need this data, why don't you have it in the first place? So typically, you need to access n bytes, every single byte at least once. Then there are two obvious lower bounds on the time to complete the algorithm, the entire algorithm or a single iteration, depending on which are you talking about. So one is the limitation that stems from the processor performance. So the algorithm performs C flops, but the processor can do only so much flops per second. You simply divide this by the peak processor performance, the peak flops. So the execution time of the algorithm of a single iteration cannot go below this number, obviously, right? And the same argument holds for memory. So because n is much larger than the cache, which we are assuming. And so most, if not all, of these data must come from the main memory to the processor. So if the maximum bandwidth between the main memory and the CPU processor is a certain number, then yeah, the algorithm's execution time is clearly lower bounded by this number, right? So you need to move n bytes from the main memory to the CPU at least once. And CPU can move data from the main memory, yeah, only so fast, right? So you clearly have two different lower bounds. And when you look at the actual algorithm, then the latter is much larger, and such algorithms are collectively called memory-bound algorithms. So order n algorithm or order n log n algorithms are almost always memory-bound. So this sparse matrix vector multiplier, it is a very simple, typical example of order n algorithm, right? So given n elements of non-zero elements, it performs only flops, which is proportional to the number of non-zero elements. So right, so it's a very typical order n algorithm. So there's a alternative way to understand this, both from the perspective of algorithm and both from the perspective of processor design. So the algorithms being memory bound is equivalent to say n over the memory bandwidth is much larger than C over the peak flops of the processor. If this lower bound is much higher than this lower bound, then the algorithm is limited by the memory boundaries. So just moving these terms around, where it is equivalent to say C over n. So flops over n data. So the compute over data is much smaller than the peak flops, the compute capability of the processor over the memory moving capability of the processor, or the between the memory and processor. So the left-hand side is actually the characteristics of the algorithm. So how much this algorithm computes, and how much this algorithms, how much data this algorithm manipulates, right? So this is the characteristics of the algorithm. And for example, if you take a look at the sparse matrix vector multiplier again, C is just a couple of times of n, right? So this is a very small constant. And the right-hand side is the characteristics of the machine. So how much the machine can compute if the data is already in the processor, and how much data can be pumped into the processor from the main memory. So this is the processor's characteristics, which is often called byte per flops of the machine. On the other hand, it is this left-hand side is characteristics of the algorithm, which is often called the arithmetic intensity or compute intensity. So how intensively it computes on a given amount of data. So generally speaking, an algorithm is memory bound if arithmetic intensity or compute intensity is small, which means that it doesn't compute much given the same amount of data. Well, in other words, it's in a way efficient, right? So it's order n or order n log n. Yeah, this term becomes small. And on the other hand, that the processor, this is the processor's characteristics. this part, the peak plots, tends to be in a way sort of inflated compared to the memory boundaries that the processor has. So it is sort of, well, inflation may not be the right word, but it is in a way increased by simple means such as SIMDs. But the hard part is actually how you move the data from the main memory to the processor. So all in all, these memory-bound algorithms are very difficult to get efficient from the perspective of the processor. But I should note that the algorithms being memory bound is not necessarily a bad thing. So it's not a good thing from the processor's perspective. So it's not good in the sense that you cannot achieve excellent flops performance that is close to the processor's peak performance. But from the more holistic perspective, whether this algorithm is overall a good algorithm or not, well, it is often a good algorithm. So it is achieving the goal without doing too much computation for the given amount of data. But just purely in terms of whether you can get close to the peak performance, memory bound algorithm is of course, in a way very challenging. It's not. It doesn't get a good performance from the processor's perspective. So I talked about the sparse matrix vector multiply just as an example of a memory bound algorithm. But actually, whether the matrix is sparse or not doesn't matter very much. So the thing is actually true even if the matrix is dense. So let's consider A multiplied by another vector, but this time assuming A is actually dense, it's actually just a two-dimensional arrays. So all the elements are materialized in the memory. So the program looks like this. Well, actually, the same argument, pretty much the same argument applies primarily because a single matrix element is worked on only once throughout this double loop, right? So this doubly nested loop is essentially scanning the entire A, right? So this time, well, it's slightly different because you are literally scanning the entire 2D array. But the fact remains true that a single element is worked on only once. So just to calculate more specifically, so the entirely it's doing m by n flops, right? But on the other hand, the data, the amount of data it needs to touch at least once is mn plus m plus n, right? So y, so m elements for y and n elements for x. But these two terms actually do not matter very much. So the only thing important is, yeah, you have mn elements of A and doing only mn flops. So it should be 2 mn flops or mn FMAs, right? So the fact remains pretty much the same, that you perform only mn flops over mn FMAs over mn different elements. So it's still, so in terms of the arithmetic complexity, it's exactly the same as sparse matrix vector multiplication case. So things become different when we talk about dense matrix multiply rather than matrix vector multiply. So this is different. So the same argument does not apply to matrix multiply. So that's actually the reason why I have been talking a little bit deeply about this matrix multiply and give you this problem as an exercise. So let's analyze how many computation it does and over how much data. So let's consider C plus equal A by B, and these matrices being this slice and K. So for the sake of simplicity of the argument, let's make all three equal to n. So it's just an n by n matrix. So multiply two n by n matrices, and to get another n by n matrix. Sorry. So let's assume that all these matrices are square. Then, so the number of FMAs it performs is n cubic, right? N to 3. And the amount of data it needs to touch at least once is 3n squared, right? So the point here is this is much larger than this. So this is n cubic, and this is only n squared. So this kind of algorithm is very arithmetically intense or computationally intense. So if you compute this term, it is much larger than a sparse matrix vector multiply or a dense matrix vector multiply for that matter. So we can hopefully get this much larger than the right-hand side, which means that the performance is now bounded by the processor performance, not a memory performance. So, but actually it doesn't happen automatically. So for example, if you simply do something like this, the most straightforward triply nested loop, the fact remains true. So if you look at this a single statement of the innermost iteration, the fact remains true that you need to access 3 elements and perform only a single FMA. So even if the algorithm in its entirety has a large compute intensity, well, it does not necessarily mean it happens, or it becomes limited by the processor, not limited by the memory automatically. Well, it does not necessarily mean that. So the basic observation is that, for example, if you take the innermost loop, you can observe that Cij is always the same element throughout the entire loop of this innermost loop, right? So in other words, the same element C is reused many times again. So if you look at the entire algorithm, right? So if you look at microscopically only a single statement, it still accesses 3 elements and performs only a single FMA. But if you look at more broadly. For example, if you look at the entire innermost loop, well, actually, the same seed is accessed many times. So it is hopefully staying on the cache, and even better, you can allocate a register for this element Cij in the innermost loop. So this is how you can make things efficient. So without going all the way to the main memory every time, you can hopefully access get the same element either from cache or even registers, depending on what the program actually looks like. So actually, all of these elements are used n times if you look at the entire algorithm. So chances are that when you order all these n cubic FMAs in a clever way, chances are that many of them hit on the cache. So the many of these data can be delivered from the cache without going all the way to the main memory. So this is how dense matrix multiply could be made efficient. So again, I need to emphasize that it doesn't automatically happen. So it doesn't happen in this simplistic triply nested loop. So in the end, you may want to change your algorithm so that it is very efficient in terms of the memory accesses too. And actually, so this matrix multiply is a very important building block in many applications. And nowadays, especially for deep learning. So deep learning is doing many matrix multiply. So if you make it faster, then you can make many of the deep learning algorithms faster. So of course, it is already built into many frameworks and libraries, but it's still fun to apply many knowledges you actually obtained in this course to make some useful deep learning application faster. And I hope you will enjoy doing this in later weeks. Okay, I think it's almost time to finish. So if you have a question, you can ask now. So otherwise, I think it's done for today. So see you next week.